So in summary, we have found that for each observation, we can find it whether it's beneficial or detrimental and can avoid large skill dropouts due to detrimental observations. And we are working with a modest wind scientist to find and correct the problem that we have identified. And there are other problems in other observing systems, like the profilers, for example. And this can be used to implement the assimilation of new instruments much more efficiently than the present approach of computing many 5-day forecasts to see if there is a tiny improvement in the forecast. That's a very inefficient approach to test. And I'm quickly running out of time, so I'm going to quickly go over the idea that Daisuke Hota estimated how to compute the change of the detrimental or beneficial observation depending on the size of the R, which is the error covariance of the observations. And he made a very simple experiment, and he found that, for example, AMSU and other radiance observations have a very, very positive dependence derivative of the with respect to the error covariance. So he said, if we reduce the error variance, we should, for these instruments, we should improve the forecast. And he actually made a very simple forecast, and the errors in blue, which are the new ones, are always, sorry, in the red ones, which are the new ones, are always more negative than the previous ones. So they improve the forecast. So this is very promising. And I guess I will quickly go over this idea how to estimate and correct the model bias. And this is an idea that's being developed by Kriti Bhargava, a student of Jim Carton and myself. And we are grateful to these people. And the idea is that the analysis is the first guess minus the forecast. So if we take the time average of the analysis, is or the analysis increment, which is the difference between the analysis and the 6-hour forecast, the time average should be the best estimate of the error growth due to the model bias in 6 hours, because the 6-hour observations are trying to correct. However, the analysis increment may also contain observation biases. But so we did some preliminary experiments with the speedy model with Danforth, myself, and Miyoshi, and we got very nice results. We estimated the 6-hour bias in a way that was similar to analysis increments, and then when we corrected the model itself, we changed the equations of the model, subtracting the bias that was estimated. We found that correcting it online reduced the errors, as it's shown in blue, all the time. And what was unexpected, perhaps, but true, was that the random errors were also reduced by the online model corrector. Not just the bias, but the random errors. So we corrected the model so it was better, and then the random errors were smaller. And we found a way to estimate the diurnal cycle. And so we Kriti Bhargava with Jim Carton and myself is working on the ENSEP global forecast system. And sorry. So we estimated the analysis increments, and let me just skip to that. So what we got was, for several years, the 6-hour forecast and the analysis. So this is the analysis, this is the 6-hour forecast. And if you look at them, they look completely identical. But if you subtract this minus this, which is the correction that the observations are making on the analysis, you find that there are very well-defined average errors or estimated errors, both for January and July, and they are different and they are very well defined. So they are not random. And if we look at different years, 2012, 13, 14, for example, if we look at the summer of the Northern Hemisphere errors, they are almost identical. So they are very, very robust. So this suggests that the model has a problem, or maybe the observations are biased, but this is something that could be corrected. And we also looked at the diurnal cycles of the errors and found that with the 4 leading EOFs, we could capture the diurnal cycle essentially perfectly. So this is what we get with 4 modes, and this is what we get for the diurnal cycle for the full modes. And maybe it should be identical, because this is the definition. So it suggests that we can estimate and correct very clearly the diurnal cycle errors in addition. And so one last thing is that we found that actually in 2015 and 2016, the errors were reduced compared to 2014 and the previous years. And it was, for example, you can see that this is smaller than this, and this is about the same. So something happened in 2015 that reduced the errors, especially over ocean, and Kriti found that it was the use of better estimations of the sea surface temperature. So the sea surface temperature was Reynolds weekly averages, and that had systematic errors, and these were corrected. So this indicates that one has to correct the systematic errors in the observations, not just the model. And so basically, she's now testing introducing the correction of the errors of the temperature, and she has not yet worked with the velocities and the moisture, but as the latest I heard from that was that the model didn't blow up by correcting the temperature. So that already makes me happy, and I think we will be able to correct the systematic errors substantially with this method. So, well, this is work that Travis Luca is doing mostly with Steve Penny here, and myself and Takemasa, and it's a strongly coupled data assimilation, and when we do data assimilation for the atmosphere and the ocean, typically until recently we assimilated the atmosphere, we assimilated the ocean observations in the ocean, but we didn't actually couple them. So what if we ask, should we do coupled data assimilation? The answer doing toy models is yes. In a toy model, coupled ocean atmosphere model, strongly coupled data assimilation was best. And but currently we assimilate separately the ocean and the atmospheric observations and then couple the models. So the observation, the atmospheric observations influence the atmosphere, the ocean observation influence the ocean, and then the models are coupled and they drive each other as they like to do. And that's what we call weak coupling. And so we proposed strong coupling, that the ocean sees the atmospheric observations and the atmosphere sees the ocean observations. This is a work that has been published, I guess myself also, in a paper. This one of the most pioneering examples of data assimilation is done by Xiaoqing Zhang at GFDL. He coupled, he did ensemble Kalman filter for both the atmosphere and the ocean, and the atmospheric model only assimilates atmospheric observations, and the ocean model only assimilates ocean observations, and then the models are coupled and it's run. And this is what we call weakly coupling, because the atmosphere doesn't see the ocean observations. So what we proposed to do, and this was more developed by Miyoshi and Penny, was to have the ensemble of coupled ocean atmosphere models, and they give the forecast to the LTKF, and the observations are here, and they are localized. So, for example, these observations can be seen by both the ocean and the atmosphere. So, so the ocean can see atmospheric observations, and the atmosphere can see ocean observations, and then the LTKF does its magic, and it continues. And Sluka et al. In GRL published the first example, I think, of, or one of the first examples with this relatively realistic system, which is speedy, coupled with the NEMO ocean model. And these were perfect model OSIs. And the weak coupling was used as a control, what we use standard, which is the atmosphere assimilates atmospheric observations and the ocean only ocean observations. So after that, he tested strong coupling. The ocean saw the atmospheric observations, and the atmosphere sees the ocean. And he only got to do just atmospheric observation. So the control was weakly coupled data assimilation. So since there were only atmospheric observations, the atmosphere assimilates the atmospheric observations, and the ocean just gets driven by the atmosphere. And then strongly coupled data assimilation, in which the ocean also assimilates these atmospheric observations. And we tested with a speedy model our simple Raywing zone and satellite observations, simulated observations. And let me show you the maps, because they are more clear. This is the difference between the error of the strongly coupled minus the weakly coupled. So negative is good, because it means the strongly coupled has smaller errors than the weakly coupled. And the results are very, very encouraging, as you can see. It's almost always blue. And curiously, when he used atmospheric observations only, the maximum impact happened at the tropics. And when he used ocean observations only, the largest improvement happened in the extratropics. And this completely surprised me. I expected the opposite, because in Malakia's PhD, he showed that, oh, that's 5 minutes. Okay, Malakia showed very clearly that the ocean tends to drive the atmosphere in the tropics, and the atmosphere tends to drive the ocean in the extratropics. But actually, if you think this result, which is was very surprising to me. It's actually to be expected because the model itself knows how to use the ocean observations very well in the ocean and the atmospheric observations in the extratropics. So the model does it can extract the information from the observations in the tropics for the ocean observations and the extratropic for the atmospheric observations. But the data assimilation complements that. So what this does is, what this is saying is the data assimilation, the strongly coupled data assimilation complements what the dynamics of the model would do. So they have the opposite effect. So now he has started doing real observations, and he's using the NCEP CFS model with real observations, and he used observations shown here, and he got actually that the weakly coupled data assimilation had very large ocean bias to warm and also atmospheric bias in the summer of the northern hemisphere close to the coast. And I think Jim Carton may explain these biases himself. So this was the result of the weakly coupled, and actually he plotted the covariances of the atmosphere and the ocean in June and December, and also the mixed layer depth. And you can see that the covariance is very large until above the mixed layer depth. So one should not localize like he did with smaller values. So he did strongly coupled data assimilation, and actually he had a big reduction of the errors, as I think I've seen. Yeah, this is the weakly coupling, and it shows these large biases near the surface, and this is when strongly coupled, and that the difference between the strongly coupled and the weakly coupled is blue, which means it's better. So the ocean improved its bias because it assimilated surface atmospheric observation, and in turn the improved coupled ocean model reduced the atmospheric observation, so both the ocean and the atmosphere actually improved. And he concluded, well, he then made more experiments, and then he found that the strongly coupled was better only near the surface, but at lower levels it was actually worse for the northern hemisphere summer. So you can see it's blue at 5 meters and 15 meters, but at 25 and below it's red, which means it got worse. It's in this part. So he thinks that it's because he should use the localization of the use as a physical localization, something related to the mixed layer of the ocean, and the ultimate goal that perfect timing. The ultimate goal is to have coupled, strongly coupled data assimilation of the whole system, but this figure is actually missing the most important component of this system. You know which is the most important component of this system? It's not plotted here. it's the human system. The human system is dominating everything, and we have to include it in the coupling. Okay, thank you very much.